This is Daniel Romanowski. Our group's analytical research report is about issues with quantum computing. This report is prepared for Professor Ellis of New York City College of Technology. Quantum computing is a new technology which is still in the research and development stage and has many issues yet to be solved. Qubit observation, lack of programming languages, and cybersecurity in classical computers interacting with quantum computers are some of these issues. Development costs not delivering a return on investment is also an issue, with quantum computing having a long way to go before hitting the mainstream market. This report aims to investigate and explore current issues relating to quantum computing as well as solutions to those issues. Through the use of qualitative methods of research, this report will first define a quantum computer and its shortcomings, and then describe quantum mechanical features. It will also explain the history and current state of quantum programming languages, explore the cost of a quantum computer, and analyze concerns relating to quantum cybersecurity.
Hi, my name is Lia Barbu, and I will try to explain why we choose to research quantum computing for our paper. It is a re-emerging technology that comes with a big promise to process information much faster and more efficiently than the most powerful computers we use today. It comes with high information storage efficiency, privacy when surfing the internet, powerful quantum information processing capabilities, and the fastest way to solve troublesome problems. Every day, we hope to read in the news that there has been a breakthrough with quantum computing, and quantum computers will soon be available for the consumer market, but our research shows that this may not happen soon. Even though a lot of significant steps are made in the right direction for quantum computers to become part of our daily life, like the classical computers are for us today, quantum computing has to overcome some notable concerns, which will be discussed in this presentation.
Hi, my name is Jinkwan Tan. Um, Today I'm gonna explain what is quantum computer is. So a quantum computer composes of software that process quantum information such as quantum algorithm and quantum coding, and use special hardware like quantum transistor and quantum memory chip. Quantum computers are, according to what C said, physic- is a physical device that can perform high-speed mathematical and logical operation that and can store and process quantum information following the laws of quantum mechanics. When a device processing and calculation are based on quantum information and runs with quantum algorithms, it is a quantum computer. The concept of the quantum computer stems from research on reversible computers. The purpose is to address the issue regarding energy consumption of computers. A quantum transistor energy is a pass through an electronic device at a high speed movement to break through the physical limit. The switch of the quantum transistor and the transistor speed control switch has allowed a chip operation ability more than normal, and the use of environment adaptability that is very strong. A quantum transistor is indispensable part of a quantum computer. Quantum memory is a kind of memory with high information storage infection. It can assign value to any computer computation information in a very short time. It is a dis, indispensable part of quantum computers and one of the most important part of the quantum computers. The factor of a quantum computer is a large control system. which can control the operation of the component. This component occupies the main position in the development of quantum computer. It plays an important role in an application. Quantum computers have a powerful quantum information processing capability. For the current changeable information, it can extract affected information and process it to make it become new and useful information. Also, quantum computer use qubit, a two system, a two-state system can be both 0 or 1 or can be 0 and 1.
Hey everyone, this is Emmanuel Arias. As Daniel mentioned, one of the issues we face as quantum computers development continues to make steady progress is the threat they pose to classical computers, the type of computers we use daily. Quantum computers are capable of performing lengthy mathematical and logical operations at high speeds. Their processing power poses a threat to the current encryption standards we use today. They are not complicated or lengthy enough to hinder the performance of a quantum computer. Lamont Wood, a freelance journalist with over 3 decades of experience writing about high tech, details a hypothetical scenario in which a classical and a quantum computer are pit against one another to crack an encryption algorithm. Assuming you can amass enough processing power to test 1 trillion keys per second against a system that uses a 128-bit AES, also known as Advanced Encryption Standard, it could take a classical computer 10.9 quintillion years to crack the cipher. On the other hand, it could take a quantum computer 6 months to crack the cipher, Wood says. With quantum computers estimated to be on the market for enterprise use within the next 20 years, enterprises must begin to future-proof their systems.
Hello, my name is Nikita Clark, and I'll be going over programming languages for quantum computers. Similarly to computers we use from day to day, quantum computers need programming languages so that the hardware and software can interact with each other. These languages are referred to as quantum programming languages. The earliest notation of quantum programming languages was in 1936 and the work of Garrett Berkoff and Jean von Neumann, who focused on quantum logic. Fast forward to 1996, where Emmanuel Nil created quantum pseudocode, the first practical quantum programming language. In 2003, Bernard Ermer developed the first groundbreaking quantum programming language called quantum computation language. There has been some semblance of progress where researchers and scientists are creating languages while the concept of quantum mechanics are not yet solidified. This is an issue because without a blueprint of quantum mechanics, researchers and scientists are providing great margin for unforeseen errors, plus the potential loss of time and money. It is understandable that researchers are trying to find alternative ways to progress quantum programming by utilizing virtual quantum machines on traditional computers. However, the issue lies with being able to account for quantum accuracy on a computer that's science-based versus the accuracy on a computer that's quantum mechanics-based. On a more linguistical approach, data types have not yet been fully realized in many of the current offerings of quantum programming languages. Where traditional computers, like the ones you and I use today, have data types for integers, floating point numbers, and characters to process mathematical logic. Quantum programming languages do not contain data types for quantum logic, such as matrices, gates, and operators.
Organizations have to consider the cost of the components and the resources needed to maintain quantum computers. Before manufacturers are able to offer quantum computers to the consumer market, they have to find ways to improve the development cost. The biggest expense is due to the fact that quantum systems are fragile and need a controlled environment. Researchers are looking for ways to decrease this cost, and one solution found is to increase the temperature at which quantum computers function. This will reduce the cost of refrigeration, which will then reduce the cost of development, bringing quantum computing closer to reality.